You see the screen? Great.
Fine. We see your presentation. Yeah. So please go ahead. Yeah.
Great. Thank you. And welcome to the last talk of the day. I would like to talk a little bit about joint work we did with Niek Bouman on a practical approach to the secure computation of the Moore-Penrose Pseudoinverse. We have a little motivating example to start with. So imagine there are 3 hospitals that wish to perform some kind of linear regression analysis on their combined databases of medical data. But for legal reasons, they cannot share their data directly with one another. And how are they going to solve this problem? Of course, they use secure multi-party computation. And they will use our protocol for securely solving systems of linear equations. And it is this protocol that this talk is about. As the third talk in the MPC session, so I'll try to give a brief introduction. In a secure multi-party computation, or MPC, you're dealing with a setting in which there are multiple parties that each hold some kind of private input. And these parties would like to compute some function on all the inputs put together, but they wish to do so in a secure manner. Now, I won't go into formal definitions of security, but for the purpose of this talk, think of that they want to keep their private inputs secret from one another. Also, let's not forget that the computation must return the correct result. And I won't deal with any other security properties that might come up in MPC. Okay. We've tried to keep our protocol, let's say, a bit agnostic of exactly which kind of secure party computation we are using, concretely think about MPC based on secret shared data, which is secret sharing is a method by which multiple parties can sort of have a handle on data, but they're actually not able to inspect anything about these data. From their point of view, it's as if they're looking at random numbers. However, by working together, they can still perform meaningful operations on these data. Now, anytime secret shared data pop up in these slides, I've denoted them with these double square brackets. So here in the top, we have a secret share value x. We target MPC in which arithmetic is performed over a finite field, in fact, a prime order finite field. So concretely, you must really think of the integers modulo prime p here. Now, as for operations on secret shared data, there are some elementary secure operations that you can carry out on them. So we have some arithmetic, addition, subtraction, multiplication, what have you. There's also, there are protocols for secure zero testing to test whether a secret shared element is zero, to sample random elements such that none of the parties really know what the random element is, but they have secret shares of it. Very important is also how to reveal secret share of data so that they can actually make a secret data known to the parties. And for the purpose of this work, because we will be dealing with linear algebra, an efficient dot product is also interesting for us. And for example, MPC schemes based on Shamir secret sharing offer a very nice efficient dot product that is essentially, in terms of communication, just as expensive as a single multiplication. Now, you can take these elementary operations and put them together to create, let's say, composite secure operations, secure protocols. But in doing so, you must be careful that the algorithm you're putting together is oblivious. And that means that the behavior, the observable behavior of the algorithm must be independent of any secret inputs. For example, an oblivious algorithm cannot perform any conditional branching based on secret data. So I think at this point, we're ready to put our problem a bit more precisely. And and that is that in our work we aim to find a practical, secure protocol that, given a secret shared system of m linear equations in n variables, determines a secret shared solution without revealing any information other than the system's dimensions. And I've also repeated it here in symbolic form to really make clear that we're dealing with an input matrix and vector whose shape and whose dimensions are known to the parties, but it is the coefficients that are secret shared between them. And also that we want to create a protocol where both the input and the output are secret shared, so that a protocol for solving linear systems can itself then become a building block in bigger composite protocols. Now, MPC has been around for several decades by now, and we are hardly the first to take on linear algebra in MPC. So how does our work relate to existing work? We've identified mainly two lines of work. And the first is a line that was initiated by Kramer and Dampoort in 2001. And this is linear algebra in a very general setting. Basically, there are no assumptions on your inputs. The protocol should work for any kind of input matrix, and there are also similarly no assumptions on different party roles. So it's very general. And their protocols also achieve the theoretically very valued constant round property. However, they pay a price for that, and that is that their communication complexity is rather high. It's n to the fifth or to the fourth here in terms of the dimensions of the matrix. And furthermore, there's another problem that pops up, which is that they perform exact arithmetic over the finite field. However, for linear algebra, the results over a finite field do not always correspond to results over real numbers, which is of course a problem if you want to use these results for any real world application. Then there is a second line of work. It's more recent, and it targets solving systems over real numbers, having approximate arithmetic over the reals, either by a secure fixed point or secure floating point arithmetic. However, these works are less general than the line of work of Kramer and Dampoort, in that they tend to make assumptions on the matrix, or such as that it can only work for full rank systems, or introduces different party roles or security assumptions on how these parties behave among each other. Now, for our work, we would like to achieve the same level of generality as Kramer and Dampoort, but we would also like to target real numbers, and we do that by performing exact arithmetic. I say your exact arithmetic over the rational numbers, but it's exact arithmetic that can be interpreted as a result over rational numbers. We also have no special structure assumptions on the input matrix or any special party roles. Unfortunately, we don't have constant round complexity. We have some linear round complexity, but in return we get a much lower communication complexity, which is essentially cubic in the dimension of the matrix, with actually very small constants. So it's, we deem this rather practical. And if you take the efficient dot product that I mentioned into account, you can even state the communication complexity as being square in the dimensions of the matrix. So in this talk, I do not want to give you a full description of our protocol, but instead I would like to dig a bit deeper into this problem that I mentioned a couple times already of computation over a finite field with results that should be meaningful over the rational numbers, or let's say for real purposes. One of the things when dealing with finite fields is that your field should at least be sufficiently large to represent both your input and your output. So you have to be able to represent the matrix A and vector B, but also at least some solution to the system X must be possible to represent that in your finite field. Now, on top of that, linear algebra over finite fields is slightly weird, let's say, compared to what we're known to over real numbers. And some of these weird problems pop up from now and then, such as over finite fields you can have vectors that are orthogonal to themselves. And a third problem is when dealing with systems that have multiple solutions. And I would like to look a bit closer at that with an example. So remember that in general, if you have a system with multiple solutions over the reals, in fact, then you would have an infinite number of solutions. And you can describe those solutions by taking any particular solution you like. And if you add just any vector from the null space of your matrix, that would also be a solution to the system. So here on this slide, I've given a very small system. And on the right, you can see the solution, which is over the rational numbers, is this blue line. Now, if we were to take the solutions to the system over the finite field of integers modulo 7, which I've written out here, but you also get these 7 dots that are in the picture. And you see that only the 3 dots that are on the line do really directly correspond to the solution over the rational numbers, and the 4 remaining dots. Now, in general, it is the case that most solutions that you would get over a finite field do not directly correspond to solutions over rational numbers. So how can we deal with this? We actually turn to the Moore-Penrose Pseudoinverse. The Moore-Penrose Pseudoinverse, or just pseudoinverse, let's say, is a generalization of the inverse of a matrix that obeys these 4 equations here at the top. And the great thing about the pseudo-inverse is that it is unique, and it gives the minimum norm solution. So in case you have multiple solutions, it actually gives you a solution that is closest to the origin, let's say, in some sense. And if you choose your parameters right, this is exactly one of the solutions from which you can recover a solution over the rational numbers. Now, as a little bonus property, let's say, even systems that have no solutions, you can compute the least squared error solution with the pseudo-inverse, which is basically the vector closest to the solution in some sense. So it's a very useful notion, this pseudo-inverse. Over the rational numbers, the pseudo-inverse always exists. But when it comes to finite fields, you do have to take into account, again, this slightly weird notion and problems due to self-orthogonality. So it only exists if you satisfy the condition on the bottom line here, which is due to Pearl more than half a century ago. Okay. Now, there's another attractive feature when it comes to computing with the pseudo-inverse. And that is that the denominators of all its coefficients can be taken together in one common denominator. But this is actually not, it turns out that this common denominator is of the same size, let's say, as all the numerators in the matrix. So it's relatively well behaved. And there exist methods to compute this denominator efficiently. So what we would like to do is to represent our pseudo-inverse over the rational numbers, and it's actually a pair. We compute the pseudo-inverse over a finite field, but we also keep track of this common denominator. And then I have a little figure here to then show our strategy. Let's say on the left we have the plain text world and linear algebra, so that as you can practice it in plain text. And on the right we have our secure world with the things we want to do. And at the top left there is the input matrix A over the integers, and you would like to compute the pseudo-inverse over the rational numbers then. Now, if you pick your modulus large enough so that you can represent your input, then there exists this identity mapping between the integers and the elements of the finite field. That's displayed on the top line. Then, if you apply our secure pseudo-inverse protocol, you would get a secret shared a secret share of the pseudo-inverse over the finite field. But suddenly, this mapping between the rational numbers and the finite field is gone. So the way we can recover that is exactly by multiplying by this common denominator, so that we scale up the pseudo-inverse, and now the scaled up matrix is again a matrix over the integers. And with as long as your modulus is large enough, you can directly map those two onto each other. So that gives us a way of representing the pseudo-inverse over rational numbers in a finite field. Now we've talked a bit about that you need to choose a suitable modulus size. There's actually a bound by Springer, which is displayed here, which gives you that basically states that if your modulus is larger than this bound, then you can represent all the let's say integer coefficients of the numerators in your pseudo-inverse matrix, and also that common denominator. Now, as you can see, this bound depends on the dimensions of the matrix. I define mu as the minimum of the dimensions, but it also depends on the Frobenius norm of the matrix. So it is in some way dependent on the entries of your input matrix, and this approach is therefore limited to settings in which you can bound the size of the Frobenius norm of the input matrix. Now, I do want to say that this problem holds for any approach in which you want to compute either the pseudo-inverse or a minimum norm solution to a system over a finite field, and still be meaningful over rational numbers or real numbers. So also the works of like Kramer-Damgaard and Kamerkiels and Padot are subject to this condition. Then finally, I would just like to give a very brief sketch of how our protocol then works in the end. We actually compute our pseudo-inverse with an intermediate step by first computing a so-called reflexive generalized inverse of a particular matrix. And here I've highlighted in blue this protocol ALIM, which computes the reflexive generalized inverse. We compute that using a block recursive elimination protocol that is itself composed of these elementary operations that I showed in the beginning. We use a randomization technique so that we randomize the input to this ALIM protocol and that way it basically deals with an average case input and does not have to deal with any exceptional input, which would make it more difficult to make such a protocol oblivious. Of course, the randomization can be undone after the after the protocol ILIN is concluded. And then to actually compute the pseudo-inverse, all you would have to do is simply evaluate the formula that is displayed here, which you can again do with just the elementary operations. And I'd also like to show that this this common denominator can be evaluated as a relatively straightforward formula again. And I would like to leave it at that. Thank you for your attention, and if there are any questions, I'll be happy to answer them.
Okay, thanks a lot. Let me show myself. Okay, we have time for a very quick couple of questions, in case. Okay, so I also don't have question this time, so I beg your pardon, but you know, it's a field very, very far from mine, so I beg your pardon for this. So if there are no other questions, I think that we can conclude here this 7th session of the ACNS. Okay.